Okay, guys, this is a little unit that we're going to discuss, in which we're going to discuss torque. Torque. So, if you think about it, up until this point, we've spent a lot of time discussing rotational analogs to linear quantities. So, for instance, we had theta, which was our analog to position x. We've got omega, which is our analog to velocity. We've got alpha, which is our analog to acceleration. And now we have I, which is the rotational inertia, or the analog to m. And torque, which is the Greek letter tau, it's like a little squiggly t, is our analog for force. So this is the rotational analog of force. So this is the rotational analog to force. So let's think about this a little bit. Maybe the easiest way, sort of the classic way to think about starting talking about torque, is to imagine a door. So let's say we've got this great big heavy door right here. So heavy door, and it's on a hinge right there. That's the hinge, and maybe we've got the doorknob is right there. Let's try that again. I'm going to put it right there. Here's the doorknob, exaggerated slightly. And so this, right, the hinge right here is the axis. The hinge is the rotational axis. And let's imagine that you are standing, let's say this is you right here. We're looking down on you. This is, by the way, yeah, this is a downward view of the door. Hopefully that was obvious. And here we are looking down on you, and you grab with your right arm here, and you go ahead and you pull on the door like this, such that there's a force on the door in this direction. So you're pulling F in this direction. In other words, your F, your force now, is making an angle with the plane of the door, right? So there's an angle right here, and we're going to call this angle right here phi. So there's an angle phi. And maybe it's obvious, if you think about this, that not all of your F, if you pull on the door in this manner, not all of your F is going to open the door. So there's a component of F right here. That's the what we call the radial component of F. It's along the radius of the door. As this door swings in a circle, the door itself acts as the radius of that circle. So this is the radial component of F. That does not go to open the door, right? If you just pulled in this direction, in the radial direction, the door would not swing open. It's this component right here, the tangential component, Ft. It's this component, Ft, that actually opens the door for you, right? And I think you should be able, I think you might be able to see that relative to this angle phi, Ft then is equal to F sine phi. So F sine phi, this is the tangential component, the part of the pulling force F that actually goes to open the door. So this is the piece right here that's going to be related to torque. So we'll come back to that in just a minute. Before I finish the explanation of torque, I'd like to think about the location of the doorknob on the door. Right, the doorknob is almost always located way out here, far away from the axis. And why is that? What would happen, for instance, if we put the doorknob here? You could imagine a door where the knob was very close to the hinge, right? It's pretty obvious for a variety of reasons that's not good. One of the reasons is it might be apparent to you that it's sort of hard. It would be hard if you were pulling on the door from this location, right? If you were pulling here, right? If you were pulling on the door and from this location, it would be harder to get the door to go open, right? It would be you'd have to pull harder in order to open the door. So by throwing or by putting the doorknob farther out on the door, we're making it easier to open. So something, in other words, something about the distance away from the axis, which is r, something about this distance r. Try that again. So this distance from the hinge to the doorknob, this is r. And something about r makes it easier to open the door as well. And so we can combine these to come up with an equation for torque. We can say that torque equals r, the distance away from the axis, times the component of the force perpendicular, which is F sine theta, or F sine phi, rather. And this now is our equation for torque. So R times F sine theta. So in other words, if you want to generate the most torque, if you want to be able to open a really heavy door, maybe a door with a squeaky hinge, how would you maximize the torque? Well, you'd obviously exert your force with the largest R as far away from the axis as you could. You wouldn't if you were trying to move a door that was hard to move. You wouldn't push close to the axis or pull close to the axis. You'd push or pull far away from the axis, large R. What else would you do? Well, obviously you'd make F as big as possible, right? You'd like to push or pull as hard as possible. And then you'd like, what sort of angle would you like for phi? Well, you'd like this to be 90 degrees, right? You'd like this angle to be 90 degrees. That's when sine has its maximum value, because if phi is 90 degrees, in other words, if you're exerting your force in this direction, right? If this were your F, if you applied F perpendicular, then all of your force is going into the torque. All of your force, in other words, is tangential to the circular arc that the door makes. So in order to open the door, these are the three things that matter: the force you use, how far away from the axis you apply that force, and then the angle phi. Quick word on units here. Force is in newtons, radius in meters, so the units for torque is the Newton meter, which we have to be careful about, because Newton meter, we've seen that before. We use that for impulse or momentum. This is equivalent in terms of the dimension, it's equivalent to momentum, but torque and momentum are not the same thing. So it's possible to get that confused. So don't get this confused with momentum. So for instance, well, let's just don't confuse this right now with momentum. Okay. One other way we could express this, I want to point this out. Let's imagine we had a different situation. Maybe we have this, rather than using a door, which is a familiar example, maybe we've got this crazy oblong thing. And maybe this crazy object has an axis of rotation right there. This is the axis. But maybe we're applying a force to move this thing, and maybe that force, we're applying a force right here, let's say, and we're applying that force, let's apply a force right here, and we're going to apply a force in this direction. So this is my F right here. So that's F, and we can see that R, right, is from the axis to F. This is R. So in other words, in terms of the picture here, this angle right here, this angle, I want to do that in a different color. Let's do a different color. Let's try. I'll do it in purple. If I continue out R, right, this angle right here, that is the phi. That's the angle phi. There's another way of looking at torque. The other way is that rather than thinking about the component of F that is perpendicular to R, we could think about the component of R that's perpendicular to F. In other words, this R, right, a piece of R is in this direction, and a piece of R is in the direction of F. Okay, so in other words, this is the perpendicular component of R. This is the component of R that's perpendicular to F, and this, of course, this component of R is just in the line of F, and in fact, this sometimes is called the line of action, in the sense that this is the line in which all the action happens. This is the line in which the force is being applied. This component of R, which is perpendicular to the force, perpendicular to the line of action, has a special name. It's called the moment arm. So you might hear the phrase moment arm, and the moment arm is this portion of R that is perpendicular to F, and we could calculate the moment arm by simply saying that this is R sine phi. right? If this angle is phi, so is this angle, right? That angle is phi as well. And now we could calculate torque by saying r sine phi times F. And this is another expression for torque, which is really the same thing as this. We just sort of moved the sine phi over here, which is a legal move, right? Commutative property of multiplication. So again, this is this thing right here. This thing right here is the moment arm. This is the moment arm. And you can even think about this, right? As phi approaches 90 degrees, the moment arm gets bigger and bigger and bigger, right? If phi is 90 degrees, so if this angle right here is 90 degrees, then the entire r is the entire moment arm. So the entirety of r would be the moment arm. So a little bit about torque. You'll have a couple problems to practice it, but one last thing I want to say, and we'll go over this in class in more detail, but we now have all these rotational analogs, and it might be nice to revisit Newton's second law. So let's take a look at Newton's second law. If we remember, Newton's second law says that F equals ma. And it might be interesting to come up with a rotational analog for this, which I'm not even going to give you the punchline yet. I think you probably won't be surprised when you finally get it. So let's imagine, before I derive the equation for rotational second law, so this was the linear version, right? This is linear. And we'd like to have a rotational version. So maybe we've got some kind of a ball on the end of a rod, right? So here's the rod, and here's the axis. And we've got some ball here. And this thing can move in some circular arc, like this, omega. And maybe a force is applied. So let's say we're applying some kind of a force to this thing. Maybe there's a force being applied in that direction. So here's F. That's the force being applied. And so we have this is that radial component, and here's the tangential component, right? This is the tangential component that we're actually interested in, is this component right here of that force. And so what I could say is, and this is still in the linear sense, right? I could say that the tangential force, using this equation, I can say that the tangential force, right, this component right here, tangential force is m times tangential acceleration. These are still linear values, right? I haven't even made this rotational yet. I'm just saying that the linear acceleration that this ball is going to experience is related to this tangential force. So this is the linear or tangential acceleration. But I'd like to maybe think about how we could turn this into a torque. So I could then say that torque equals m times, well, what? At times r, right? So the torque is m/at times r, but I also know that At equals alpha r. In other words, I can plug in alpha r, this thing, in for At, and then what am I going to get? Well, I'm going to get that the torque now equals m times alpha r times r. Well, I can kind of rearrange some things here, and I can write that the torque equals m r squared times alpha. And lo and behold, what do we have? This thing, that's rotational inertia, right? That's what that is, rotational inertia. That's I. And so now I can write the expression torque equals I alpha, which I think you probably guessed that that's where we were going from the get-go here, right? So torque is our analog to F, right? So this is similar to F. I is similar to M, and alpha is similar to A. So this is just F equals M times A, but in rotational quantities. We're going to start off. I'm going to start off class by doing a sample problem using this equation, using Newton's second law for rotation. It's a little bit tricky, but we'll go over it in class tomorrow.